All right, I'm going to wait till I get a feedback to see if I have audio. All right, got it. All right, got it. Okay, if we go back and look at some of the problems, we're going to see a similarity between most all of these, even into the previous section. This is one of the ones we did in class. Move into here. There isn't really that much difference. We may go do 268 in a minute because the magnitude and quarter direction of angle, so the resultant of the three forces is 0. That's pretty simple. More simpler than it seems. So all of these have a basic functional similarity. This one, however, is different. And it moves itself into the next section. And if you go back and you look at the content here, you'll see there's a fair amount of videos here in week 3 that cover this. Then if you go into week 4, you'll see the same thing. Actually, while I'm here, I'm going to go ahead and make week 6 available. If you look at week 4, you'll see actually that particular problem I just kind of referenced worked right there. Oh, it looks like it did it again. Then week 5, we move into the concept. Oh, wait a minute. Wait. We move into the concept. This is, I guess, video 3 and actually video 4, just from the panes right there. That is a pretty good representation of that. And so let's just go work this problem. This one sits on, okay, it sits right there. Obviously, what I think he wants here is the components of the resultant vector. The problem here is this. The vector itself isn't given the same way. In other words, previously it would have been given, I'm going to erase this in a second, x, y, and z. It might have been given in this way. Where this maybe was 60 degrees and maybe this was 30 degrees. In here, you see no angles at all. So this is a completely different representation. So how do we proceed? Well, the preface to that is we worked out this concept earlier of a base vector of some vector f. Base vector, or a unit vector in the direction of f, is just simply that. Now, as it turns out, the cable goes up and down through here. So if you're pulling this direction, you're pulling along the line of the cable, which basically has a significant advantage in that I can write a vector that points here. It does exactly that, points exactly in that direction. So if I want to draw a vector that originates from A and points to B, what I would do is I would recognize, well, it would run out 3 meters in that direction. It would run back 2 meters in the Y, and it would run down, going in the negative Z direction, 6 meters in the K. So now that you have this, you realize, hey, if I can use that, I can find a unit vector that goes exactly in that same direction. Eventually Octave will come up. I think I had it set to come up. Maybe I did not. Oh, wait, there it is. Oh, there it was. Octave is basically a somewhat free version of MATLAB. For example, if you look at it and go to the Octave website, you'll see that it pretty much, you can read all about it. Then once you decide, or if you decide you want to use it, you just go to the download, and you have Windows, Mac, BSD, Linux, and you can actually get the source code and compile it yourself. That's a lot of work, but so here's some of the Octave installers. You can just download those and install Octave yourself, and what you're going to get is something that looks like this. Very much looks like an a MATLAB interface. There's a lot of similarities. It was written to kind of be that. So now let's just get into the concept of using it. So now I have a vector RAB, so I'll call it RAB equals to, and what I'm going to do is represent it in a vector form like so. So RAB, where the x component is 3, the y component is -2, and the z component is -6. So if I want to look at the length of that vector, you'll find something interesting there. It is actually 7, which is kind of rare for it to be an integer, but it just so happens that a 236 vector ends up being of length 7. So if that's the case, how do I find, and why should I find, a unit vector which goes in the direction of RAB? Well, that's pretty simple why you would want to do that. If you found a unit vector going in that direction, and then multiply that unit vector times 840, you'll actually get the vector components of the force vector pulling down this rope from A to B. So let's go ahead and do that. So what we would get here is RAB over the length of RAB, and conveniently we can do that. Okay, U RAB, the base vector in that direction is RAB divided by the norm of RAB. So I get these numbers. However, instead of typing these, what I'm going to recognize is that the unit RAB is going to be 3/7 of I minus, and the reason being is because we already determined that that's 7. 2/7 of J and 6/7 of K. If we want to check that out, make sure that seems okay, we can go back here and we can just take this U RAB and just multiply it times 7 just to check. Oops. And in fact, that's what you get, 3, 2. So in fact, that's what this is, you know. The first term is 3/7. This term right here is 3/7. This term is 2/7, and this term is 6/7. So now that I have that, what do I do? Well, if I'm actually looking, and this is the key here, if I'm looking for the force in B, it's actually equal to 840. Why 840? Because he told me that's the value of this force. So 840 times URAB. Well, there's something interesting about this case, and he designs these problems this way. I would not count on this being the case. But if you take this and look at these terms, 840 times 3/7 of I minus 840 times 2/7 of J. Again, I'm pulling this one in and this one in. So this should be times and minus 840 times 6/7 of K. You'll find something very interesting here. And what you'll find is 840. Let's just check this out. 840 divided by 7 gives you 120. So what you end up with, 120. Again, what I'm basically saying is that's 120, this is 120, and that's 120. So it's 120 times 3 I minus 120 times 2 J and 120 times 6 K. But if you wanted just to carry this out without thinking too much, here's what you do. I already have U RAB. It's this vector right here. So I just take that U, I say F B, the force vector B is equal to 840 times U RAB. And that's what I get. 360 minus 240 and minus 720. So this is my force at B. That's pretty much it. So that takes care of the first one being FB. So what I'm going to do, I'm going to take that whole group of calculations, slide it to the right, kind of isolate it, and then I'm going to return back over here, and I'm going to work on C. Now something's interesting here. There's a value of 3 and 2 here, and still the same value of 6. There's 3 and 2. Turns out the length of this cable was 7. Turns out the length of that cable is 7 as well, because we still got 6, 2, and 3. We'll find that out in a second. So let's do it here. So we're looking for R, A, a vector drawing from A to C. So we want to draw a vector from here. You know what? Let's do something. Let's do that. R, A to C. So we're going to draw a vector down this cable in the direction from A pointing to C. Why are we drawing it in that direction? Because that's the direction that the cable is pulling. And what I get, okay, just do the same thing I did before. I go 2 meters out in the I. This time I go 3 meters out in the J, and I go down 6 meters in the K. So now, what is the base vector? That points, base vector being a vector, which points down this rope, say, points down this rope, but it's only of length 1. Why do I want length of 1? Because then I take that vector, multiply it times the FC of 420, and I get the actual FC vector. So here's what I'm going to do. I'm going to go in. I'm going to basically say the unit vector, or that points along AC. Is of course unit vector, meaning it's of length 1. The vector itself divided by its length. Well, it turns out that length is 7, but let's go into our octave. Here we go. RAC equals to a length of 2, 3, and minus 6. Again, if I looked at the norm of RAC, not too surprising, I get, well, first of all, if I was able to type, okay, this should have been 3. That tells you already. Very rare to get integer values out, but in fact, I did get an integer value out of length of 7. It is, you need to realize, it is pretty rare. Okay, so URAC is going to be equal to 2/7 of I plus 3/7 of J minus 6/7 of K. Now, if I want to know the force vector, okay, its magnitude is 420, but the force vector itself is 420 times 2/7 of I. You know what? I'm going to put a box right here. That might clarify it. And it clarifies it in one regard, that this right in here is in fact that unit vector, and this is in fact the magnitude of the force. Now, again, if I just want to let Octave or MATLAB take care of it, that's pretty easy. I did not find the unit vector yet. Unit vector RAC is equal to RAC divided by the norm of RAC. Again, I get some decimal values here, in which now I can basically say the force vector at C is equal to 420 times the unit vector that goes from A to C. Now, again, it is pretty rare to get these things like this, but you know, 120, 180, and minus 360. Okay. Okay, I've already forgot. 180. Okay. Now, these are my two vectors that I determined. What I want to do now, I want to add them up. FB plus FC is equal to. Now, of course, you can add them one at a time, put them down there, but I did put them both in Octave. I have FB sitting right here, and I have FC sitting right here. So I'm going to do F resultant is equal to FB plus FC, and I get that 480. Okay, so the resultant force is going to be equal to 480 I minus 60 J minus 1080 K. Now, let's start looking at some of this. What we want to do, okay, you've got this as far as a vector concerns, but you might want to know the magnitude. So let's haul off and try to find that. I have listed FR, so I can type in the norm of FR, and I get 1,000. Hang on for a second. 1,000. I'm not sure how many digits he throws away, or if there are any digits that are thrown away. 11834. Okay, so I think we're okay there. Now you might necessarily, or someone might ask you for the angles. Let me see if I can do a reasonable representation of what this would mean. Okay, so it's going to take a little bit of interpretation here. So bear with me as I try to do a reasonable job of this. Somewhere, this vector might point, say, right here. So if I were to, let me pause for a minute. I'm trying to see on these old, yeah, there was a ruler on these old ones. So if I drew that and made a reasonable representation of, say, what that looks like, this vector might point, that's the arrowhead, looks kind of funny, might point that direction. Okay, now I'm going to do something interesting. I'm going to draw, this is the direction of the x direction. And now let's see if I can do a reasonable job. Oh, I know how to do this. Go back to my ruler. Line it up the best I can with the y. That's pretty good. Then I just draw out there. I can move the ruler out of the way and say this is the y direction. I don't have to do the z. Now, to give you an idea, if I were to look at a plane here, that existed right here, then this vector, this red vector, passes below that, which means if I were to measure the angle with respect to the z to here, that would be the gamma, and that's going to be greater than 90. Then if I were to look at the angle between here and here, that's going to be the alpha, and the angle between here and here is going to be the beta. Now let's see if we can figure out how we can extract those from this. So if I'm looking for a unit vector that points in the direction of the resultant vector, that would be fr divided by the length of fr. Of course, that length is this, but I'm going to make MATLAB do that, or Octave. So I'm going to get a unit vector pointing in the direction of fr equals to fr divided by the norm of fr, and I get this set of numbers. Since in fact these don't correspond to anything probably integer-like, I'm going to do a copy, and I'm just going to do them a paste right here, just so I can keep it, but also so I can 4056i minus 0.0507j minus 0.9126k. So I'm sitting here looking at this vector. Now, it turns out, of course, the length of this vector is 1. If you want to see that, you can do that. You can look at the norm of UFR becomes 1. But here's the key. If I want to know the alpha, the beta, and the gamma, I just do cosine inverse of this vector and what I'll get is, when I'm looking at this one, the cosine of that number will give you alpha, cosine, arc cosine of that number, arc cosine of all these. And this one give you gamma. Hang on. Let's do that in MATLAB. Okay, so now I want to do arc cosine, but I want my answers in degrees of U, F, R. Okay, 66. Okay, I'm going to bounce back and forth between these two. So this tells me the first one is alpha is equal to, of course, then after that, beta, and then after that, gamma. So 66 degrees, roughly, 66 degrees, then 92.9, and then 155.87. Couple things. First thing is, wait a minute, I pass a plane. Anytime you have an angle which is greater than 90 degrees, that means you passed over that plane. Here's what I mean. The resultant vector doesn't sit right here. It sits back over here, which means that it passed behind this plane. So you make a plane right here that exists like this. That point passed just slightly behind that, which means that this angle, okay, if it laid exactly in this plane, this angle would be 90. If it moves behind this plane just a touch, suddenly you're looking at something slightly greater than 90. Of course, we talked a second ago about the fact that this vector definitely passes below this plane. And that's fine. We can see that. But I made the grotesque error of assuming that it sat in this plane. Well, I should have thought about this a little bit, because actually this is 840, much larger than the 820, which probably indicates that yes, in fact, it probably will pass below this, or behind this point will be drawn closer to this one. So in fact, the vector doesn't point to this point, it points back here somewhere. You could figure out where that points to. I mean, if you wanted to, you could find the intersection of that vector and this plane, this plane right here. And if you found the intersection of that, you'd find where that would be the equivalent, where you would want to move one of these hooks so that you'd have the equivalent force there. Not suggesting you would want to give that up, because wind loads or something could, having several of these ropes tie this thing down has the advantage of having the ability to resist an upcoming wind load that you might not anticipate. But in fact, yes, the thing doesn't pass there. It goes behind that. Let me redraw that. Maybe I can make a better explanation of that. If I have the picture down here, copy, drop the picture. Okay, so if I move this picture up a little bit, so what I'm saying is that the resultant, so imagine, if you will, let me bring the ruler back up. Imagine, if you will, that this vector passes through this plane like this. And of course, its strength of pull is 1183. So the force resultant is about 1183 and change. Well, the fact that this is 92 degrees means, now, okay, let me rephrase this. If it was exactly 90 degrees, it would sit right here. And that would be exactly 90 degrees from a line in this direction over to that one. Just so happens it's a little bit behind it. So it's a little bit greater than 90 degrees. This one, however, is, if you look at this, here's your plane sitting up here. It definitely passes below that plane getting to there. So that's fine. So I hope the geometric representation makes sense. Let me dart back and try to find out what is it this one? Nope. Is it this one? Okay, let me go back and look. It wants to know the magnitude and the direction cosine angles. Let's make sure that I got those. Okay, so he says 1.17. Okay, 1.1. I got a little bit different. Okay, so he's saying mine is this, right? I got 1.18. He got 66.9. I got 66. It's possible that he got 92. I got 92.9. He got 157, and I got 155. It's possible that it maybe slipped a digit somewhere. Or maybe he slipped a digit. I don't know. Nothing worse than slipping a digit. So that's kind of the approach when you have no angles. Now, of course, he asked for an angle, but there's a common tool that most everybody has. It's called a ruler, but it's very hard to find some type of protractor that you can buy in order to go measure these things. Now, you can get surveying instruments, but I'm saying the most common is a ruler, meaning that this is much more common as far as reality than this one. Somebody would have had to measure every single angle here in order to give you this. Less common in reality than someone telling you where this cable lands at and where that cable lands at, or rope. So that's the reason I sort of like these a little bit better. Okay, now here's a mixture. Determine the magnitude and the coordinate direction of the resultant force acting at point A on the post. It's almost the same thing. I see two of them. Takes a minute to figure out what you're looking at. Oops. Let me go see if in fact this is sitting in here. Okay, that's okay. Was I solving the one with the flag or the other one? Let me go back here. I was solving the one without the flag. Okay, hang on. Oh, looks like maybe that's it. A little bit better picture here. Okay, let's see. Let me add a new page. Now, looks like I got a mixture here. So the easiest one to deal with is at this point this one. So let's deal with it first, and then we'll move the work aside like we did a minute ago, and then we'll start working on the more difficult one. Again, if I drew a vector from point A directing straight to B, it would look like, first I would run out in the X direction 2, I would run out in the Y direction 4, and I would run down 3. Pretty simple. Oops. Let me make sure I can line these back up. Okay, so here's what I'm going to do. I'm going to clear everything out of here. Oh shoot, I don't know if I'm going to be able to remedy that situation, but I've got just the command window. I'll figure out how to remedy that at the end of this video. So RAB is equal to 2, 4, and minus 3. Now, what the next thing I'm going to do, I'm going to find a base vector pointing along. I keep saying base vector. I should be saying unit vector. So a unit vector that points along RAB, just simply this, RAB divided by its own length. Okay, unit vector RAB is equal to RAB divided by the norm of RAB, some digits. Okay, I can copy them, and I may just try to be a little bit on the lazy side here by doing this. I'll select them, and I think, do I do that? Nope, that's not it. Anyway, here's the way I'll do it. Oops. Give myself some space. And then I'll pull out the pen. Equals to this times I plus this times j minus this times k. There's my base vector. Next, I take the force. I want to find the force vector. So I find 200 times U RAB. Why? Because I'm taking the base vector. I'm taking the 200, which is its own magnitude. And now I will be able to type in or figure out FAB is equal to 200 times U RAB. There's my vector. Okay, I'm going to be lazy again. Copy. I'm going to paste it. Move this over. I don't know why. Here. There we go. And what I'll do, move it up maybe a touch. And this is going to be equal to this I plus that times j minus that times k. There's your vector. Okay. That one, moderately simple. The other one's not that bad either. Let me slide this one out of the way and designate it to be its own entity over here. And then I'll roll back. Now I got to pay really close attention to a vector which goes in this direction. Okay, so it's kind of interesting. He didn't give us an angle here, or this, or that. But what he did give us is that's a 3, 4, 5, and it's 3 over here. So you got to stare at it a minute, and you'll realize, well, that makes this distance 4. That distance, of course, he designated 3, and that is 3. So a vector R, don't know why this vector R, which originates at A and points to C, goes in the negative x direction, a value of 3. It goes in a negative direction of y, a value of 4. And it goes in a negative z direction, a value of 3. So we do the same thing. U, A, C. I'm sort of cramming it over to the left. I could have left that on the right, but I'll move it back. R, A, C. R, A, C equals 2. Now, if I didn't make a mistake, let's see. I think we're okay. Move this kind of out of the way. And this time I'll say RAC is equal to minus 3, minus 4, and minus 3. URAC is equal to RAC divided by the norm of RAC. Now, instead of me copying, I'm going to be quick about it and do this. And I'll use a combination of this and the pen like I did before, and that is I, and there's a minus sign there and a minus sign there, J, which I said J, but I wrote K. Okay, so there's your vector that points, it's a unit vector, which points in the direction of from A to C. Now he doesn't designate either one of these as being cables or ropes, but he does tell you the direction that it's passing through. So now if I want to know the force AC, it's equal to, it's 150 times UAC. So, go back to this. FAC. It was 150. He told me that was the size of it. 150 times UAC up. This should have been an R. U are in the direction of RAC. So actually, if I want to be precise about what I was doing, RAC, and that one, I'll do the same thing. Just going to copy it, and then I'm going to drop it in there. It's not letting me do anything. Okay, let me erase this gibberish. Okay, so I, J, and K, all three operating in the negative direction. So now, if I wanted to work these in tandem, then essentially all I'm doing is adding FAB and FAC. In MATLAB, that's pretty easy. F resultant is equal to F AB plus F AC. That gets me this vector. Again, I'm using the beauty of copy and paste here. So the F resultant oops, this looks funny. F resultant is equal to F. Okay, I forgot. AB plus FAC, if I'm not mistaken, and that would be I plus J and then K. Now the final thing is, what are you asking for? Well, first of all, let's take a look at the picture, and we're going to basically determine that, okay, so I'm going to copy this down, minus 2.9 I plus 45.6 J minus 188.6 K. Now, what that means to me is if I drew this, here's the reason I did this. If I did not make a mistake, do a copy, come up here, do a paste. So I'm going backwards. So if I go backwards, I'm going to basically do like so. Oh, it's not letting me. So basically run a little bit behind this, down below here, and then 45 in the J. So maybe the equivalent would go right here. A little bit, a vector might be longer than this, but it might pass through this plane right here. Be a little bit in the negative X, in the positive J, meaning it's on this side, and of course it's in the negative, meaning it's pointing down. So this would tell you that if you were going to find the cosine directions here, your next thing would be to find the unit vector pointing in the direction of FR, which would be FR divided by its magnitude FR. And then what you would want to do is you would take the inverse cosine of the UFR. That would give you your alpha, your beta, and your gamma. So if I did that here, I would find UFR would be FR divided by the norm of FR. Give me those angles, give me those values, and then I would want to take the arc cosine. I'd want my answers in degrees. You can get them in radians, that's fine, but 90. So here's an observation, okay? Let me go back. 90.8, 76.4, and 166 point something. Observation is the angle. Okay, so let's see if I can do a better job of ruler. So a vector that leaves here, passes through the plane right here. We look at the coordinates to find out. Man, that's a tough one. Turns out this vector just passes just ever so slightly behind in the negative x direction. Interesting observation. Let's force something and make an observation. What would happen if f sub r had no x component? We're pretty close to 0 relative to these two terms. But let's just force it and see what would happen if in fact we're saying that the vector passed right through here, had no x component. This is a what if. So here's what we're saying. We say fr. So this is fr not true, but what we'll do is we'll say it's 0 about we'll say just, I'm going to truncate it, 45 and then minus 188. So if you have a vector that looks like that, then you say I want to find the unit normal f not true equals to f resultant not true divided by the norm of f resultant not true. You'll see why I'm doing this in a second. You get that? Now, let's do this. Arc cosine degree of unit vector in the f not true. You get 90 degrees. What I'm saying is that is equal to 90 degrees, meaning that if in fact this vector, instead of passing just slightly behind this y, if it actually was right here, then the angle between these two is 90 degrees. And so anything that passes behind it just ever so slightly is going to be in the negative. Going to have a slightly negative value there. I don't even know if I got the right answer. I might have not. I don't know that I calculated the actual resultant, but I have 90, 76, and 177, 90.8, 76.4, and 166. If we wanted to find the here, the actual magnitude, I would do the norm of FR. I'd get the 194.06. 194. So I think we've gone over in our time a little bit, but I'm going to go ahead and drop it off at this point and say we're good. Hopefully these lectures using this thing are kind of convenient. I wish I could do the technology like this in the class, but there seems to be glitches there. So I'm going to go ahead and say it's good for now. We are passing noontime, and we'll see you on Monday.